So this is the fourth and final lecture for the chapter on Chapter 18, Aromatic Substitution Reactions. So now, in this chapter, we're going to look at synthesis strategies using everything that we've covered before, and we're going to look at two entirely different reactions. These are nucleophilic aromatic substitution and elimination addition reactions. So both of these reactions, these two new ones, involve nucleophilic attack on the benzene ring. Now, considering the fact that the benzene ring is extremely rich in electron density, it should make sense, it should be logical, that the vast majority of reactions we've covered have been electrophilic aromatic substitution. In other words, attack on the pi system. But now, think about this. What we're going to look at is a nucleophilic attack on this extremely electron-rich pi system. And so it's going to require some unusual driving forces for that. So let's look at this now. So, reviewing what you've seen so far, this is a great review sheet. 10 different groups can be installed on the benzene ring using the reactions that you've seen presented so far. And here they are. We've covered them in depth, and I've even already covered a review sheet like this. I'm not going to spend the time to go over it again. You can go back. I think that was in at the end of the second lecture that I covered this. And so, but you do need to cover this and learn, in addition to everything that you see here, all of the reactions above are electrophilic aromatic substitution reactions. These reactions below are examples of how these products of EAS can be converted into other useful compounds. So these 1, 2, 3, 4, 5, 6 reactions are the electrophilic aromatic substitution. And so you've got the reagents and the substituent, the reagents and the product, and so this shows you the substituent that is attached. So what is missing from this is the exact electrophile. And so you need to go to the PowerPoint slides, print off this slide, and write next to it what is the electrophile that is used in this reaction. And here, draw the electrophile. There's space where you can draw it. Draw the exact electrophile so that you will have all on one sheet the reagents, the product, or the incoming, the new group that's substituted, and the electrophiles. And it will be a lot easier for you to learn with all of that on one sheet to be able to review. So, let's look at some strategies. The synthesis of benzene rings requires careful analysis. So, look at these two groups. You will not add both of the groups simultaneously. One will be added first, and the other will be added second. And so this is an ortho-para director, this is a meta director, and the two groups are meta to each other. And so therefore it means that nitro would have to be put on first. And since nitro directs any other group that goes on, whatever it is, to the meta position, nitro will go on first, and it will direct the new incoming group, in this case bromo, to the meta position. So you can see this is also very useful synthetically. So if you need to have, say, an amino group on your benzene ring, the amino, you know, is orthopara-directing, and say that you need another group, meta, you would not start out with an amino group. You would start out with a nitro group, install the new group, and then convert nitro to an amino group. And here are other conversions. So this is orthopara, this is meta. This is meta. It can be converted to an orthopara director. And this is orthopara directing. This can be converted to a meta director. And so you can see how these conversions can help you put the new incoming group, whatever it is, into the correct position where it's needed in the final product. Additional considerations. The groups need to be meta, but both are orthopara-directing. And so you can put the nitro group on, have the new group come into the meta position, and then reduce the nitro group into the amino group that is needed. So let's see what that overall reaction would be. Remember, this is the nitration in electrophilic aromatic substitution. This is the Friedel-Crafts Friedel-Crafts chlorination that will put this group on. So here, this would put nitro up here. The second step will put chloro here. And then these next two steps will convert the nitro to the amino group. Nitration can't be done on a ring that already contains an amino group because the amino group will also be oxidized with the reagents that are necessary to put the nitro group on. So this cannot be synthesized through that method. Friedel-Crafts reactions don't work on a ring that is deactivated. So this reaction will not work because you've got deactivating groups on here. And that means the Friedel-Crafts acylation, Friedel-Crafts alkylation, and the chlorination. So now here we are at the first of those unusual reactions, the nucleophilic aromatic substitution. You won't see this reaction very often. So this first reaction is simply a substitution. Notice here we have substituted hydroxyl for bromo. And so this is very unusual. You do indeed have OH minus coming in and simply displacing. It is a nucleophilic substitution of bromo. However, it is very unusual, and it's somewhat of a higher temperature. And so let's look at the requirements that are necessary for this. Notice the placement of the nitro group, the strongly electron withdrawing nitro group. And so the benzene ring must possess a strong electron withdrawing group, nitro. The ring must possess a good leaving group. So here you have the good leaving group. So that's bromo. The leaving group must be positioned ortho or para to the withdrawing group. And that is because the negative charge that's generated must be stabilized by that withdrawing group, which is going to be in the ortho or para position. We'll see that. So here we have hydroxide come in and do a nucleophilic attack at the carbon bearing the leaving group. And so the pair of electrons moves into the ring. Notice now you have a negative charge rotating through in position throughout the ring, stabilized by conjugation. And so when it's in this position, here you can draw a resonance structure such that that pair of electrons comes down onto nitrogen and a pair of electrons moves off moves out of the NO bond onto oxygen. And so here is the resonance structure that is available when you have the electron withdrawing group, the nitro, in the ortho or para position. If it's meta, you cannot achieve this additional resonance structure that will stabilize that anion. And then in the last step, chloride is lost. So this is somewhat analogous to what the steps that you saw in the electrophilic aromatic substitution, where a cation was obtained in a sigma complex. This, notice, is an anion. Several different resonance structures are obtained, and this is called a Meisenheimer complex. So there are similarities, but that one is a cation, this is an anion, because this is nucleophilic aromatic substitution. So as I mentioned, there will be no reaction if this is meta, because that the resonance structure, no resonance structure can be drawn to put the negative charge here. So the phenol product that you just saw generated is going to be deprotonated. So the product would need to be quenched, just neutralized by addition of a small amount of dilute acid. Now, for the third and final reaction, if the nucleophilic, so this is nucleophilic aromatic substitution nucleophilic aromatic. So this is the nucleophilic aromatic substitution reaction abbreviation. It won't occur if the ring doesn't have a strong electron withdrawing group. So here, this reaction will not occur. But if you have a high temperature, this reaction can occur. Notice this is 350 degrees centigrade. That is very high temperature. So that is what is obtained often in a gas chromatograph oven. And so, how is that obtained? How is that reaction accomplished? So, what happens is you don't go through that other mechanism. What happens now is that you've got notice this is an amide, and so this is a very strong base. And so what happens is it actually deprotonates the reactant. So let's look here. Let me find the mechanism. Here we are. So hydroxide comes in and deprotonates. The pair of electrons moves in and forms an additional pi bond, and your leaving group departs as the halide. And so when I said an additional pi bond, notice you already have a double bond, so this becomes a triple bond. This becomes a triple bond, just like you might see in acetylene. So just like an alkyne. And so indeed, this is called benzyne, because you start with the benzene ring and you're developing an alkyne. So the name of this is benzyne. And so then the hydroxide comes in to do a nucleophilic attack at one end of the benzyne, the triple bond, and it can attack either end. It can attack either end because they are both equal. This molecule is symmetrical. Once it attacks, the pair of electrons moves down, and now you have the anion, which abstracts a proton from water. So let's go back up where we are first discussing this. So here you have the anion that's going to come in and deprotonate. And this is going to be one of the products, except you have both products, both of these products, because the nitrogen can attack either end of the benzyne. And so when you see this sort of a product mixture, and it will be 50-50, it'll be very close to 50-50, maybe 49.5 and 50.5%. So it will be very close to 50-50. And what that means is that it has gone through that symmetrical intermediate, the benzyne intermediate. So here is additional evidence for the existence of benzyne. If you label this, say, as C14 or C13, if you put a carbon labeling at the position bearing chlorine, you find out that the carbon label has been scrambled. So it will be at the position bearing the incoming group, bearing the amino group, and it will be also alpha to that, so ortho to that position bearing the amino group. So the chemical labeling, the carbon labeling, will be at the ipso position and at the ortho position. And the only way that can happen is if one goes through this benzyne intermediate, so that when the nucleophile comes in, it will come in to either position, half here and half here. And so, once again, we see it that the amide can come in at either end of the benzyne triple bond to give you the two products. This is called an elimination addition reaction because elimination occurs first, and then you have the addition to give you the product. So this is where the new substituent is added on. So elimination occurs first, then you have addition. And that's the opposite of what normally happens. Normally you have addition elimination. Here it's elimination addition. Or sometimes it's called the benzyne mechanism. So we've already discussed that. Additional evidence for this mechanism is obtained when a reaction that is believed to involve benzyne takes place. Just a little bit of furan is put in, and when that happens, the furan will do a Diels-Alder reaction, a 4+2 reaction, to give this product. So if you look closely, you can see there's the 6-membered ring, and over here is the 5-membered ring. And so it's easy to recognize that this can only happen if you have the triple bond there. Now, I might mention that the benzyne is extremely reactive, extremely high in energy, extremely unstable, and extremely short lifetime. So it isn't possible to sort of, do an NMR of it. It just doesn't exist. It just is very, very transient. And so that's why the evidence that it exists is only by viewing the products of the reaction. But it is accepted that this does exist. And so this little short sort of review chart here. So this lists the different types of reactions that you've seen in this chapter. So the first type that you saw was the electrophilic aromatic substitution, in which the electrophile comes in and does an attack on the pi system of the benzene ring. So the vast majority of reactions that you saw were up here. Then, in this last half of this last lecture on chapter 18, we see nucleophilic attack at the on the benzene ring. And so there are two different types of nucleophilic attack. You can have either the nucleophile comes in and actually attacks at a carbon atom. You have a substitution reaction, so you have an incoming group displace the leaving group. And so that was the nucleophilic aromatic substitution, and here's the abbreviation, SNAR, substitution nucleophilic aromatic. And so this was the second one that we saw. And then this third one, the elimination addition reaction, this was the one in which a strong base comes in and deprotonates benzene, the benzene ring. So it removes a proton. In both of these others, the reaction is taking place at a carbon atom. Here, the first step is abstraction of a proton. This is called elimination addition. This is the elimination addition. It does not have a stabilizing group, ortho or para, to the leaving group. And so this goes through the benzene mechanism. So it can be called elimination addition or the benzene mechanism. And so this finalizes our lectures in chapter 18, the reactions of aromatic compounds.